So I started the recording, and good afternoon, everyone. And
it's muted. Radu, you are muted for some reason.
Right. Well, good afternoon, everyone. I unmuted myself. Welcome to today's Resilience of Autonomous Systems seminar. I'm delighted to introduce our speaker today, Professor Mohammad Mousavi. And Mohammad is a professor of data-oriented software engineering. He is based at the University of Leicester in the UK, and he is the principal investigator on the UKRI Trustworthy Autonomous Systems node in variability. His main research interest is in the model-based testing, particularly when its techniques are applied to cyber-physical systems such as healthcare, automotive systems, and software product lines. And he is also interested in concurrency theory and formal semantics, and his talk today is at the intersection of these research areas on learning about the change through active learning. So, Mohammad, please.
Thank you very much. Thanks for the invitation. Thanks for the humbling introduction. And thanks to all of you for being here. I really appreciate the opportunity to give this talk. I also appreciate if you do ask questions during the talk. If anything is unclear, please stop me there and we can have a more lively discussion if you don't mind. This is joint work with two people mostly. I will cite also some other papers with other authors, but this is mostly joint work with Diego Damasceno, who was a joint PhD student with me and with Adenilson Simao. So he did his PhD at Sao Paulo, and he visited me at Leicester for a bit more than a year, I think. And now Diego has joined the group of Fritz van Drager in Nijmegen, so he's doing a postdoc there. So continuing along the same lines that we worked on before. Of course, the slides and all the mistakes in the slides are mine, and all the difficult questions can be answered by Diego. Good, so let me move on. So the talk is organized in 4 parts. I will very briefly talk about our general, say, research philosophy. What do we do in our group, which is about trust in autonomous systems. So that will be the first part of the talk. Then I will give a brief introduction to active learning. I'm sure many of you, I see some very familiar faces, know this inside out, so it will be brief, but just to make sure that we are all on the same page if we come from different backgrounds. That basically sets the scene for the 2 main contributions of this research. One is about learning about change in time. So what if you have an evolving system and that moves on in time and you want to learn about those changes in the system? The last part of the talk and the second contribution that I will present is about the change in space. So what if there are different configurations, different platforms on which your system is being deployed? How do you learn about those differences that concern the variability in terms of features and platforms? So this is the structure of the talk. So let me start with a very brief introduction about our group and what we do. We have a research philosophy, namely we would like to focus on the issue of trust and safety by using rigorous mathematical analysis techniques. And our, say, impact area, the types of systems we are addressing are autonomous systems in general. And as Radu kindly introduced, we work, of course, in different domains. Here are some of our collaborators and sponsors. And we also do lots of outreach activities to inform the public about the issue of trust and safety for autonomous systems. So we appear quite often in various channels talking about these issues, and I've listed some of the more recent appearances here. What do we mean by trust as our research philosophy? So trust is about users' belief. So it's some sort of epistemic phenomenon where the user believes that the system is not going to harm herself or himself. So the system is going to be safe and harmless, and also useful in challenging situations. So trust mostly talks about situations where the system can potentially harm, or if it does not help, it can potentially jeopardize the user's, for example, health or safety. And if the user expects that the system is not going to harm the user and is going to be helpful, then the user has trust in that system. And of course, over trusting and under trusting both are issues. So if you trust a system that is not safe, then you may damage yourself. And if you under-trust the system, you may not use it as it's intended. So both of these are important issues to discuss. And how do we contribute to trust? So the first important thing that we emphasize is technical transparency. So very often systems are designed without making those intentions explicit to the users. And one of our tasks is to make it understandable how the system has been designed. I will give a couple of examples of different projects where we've worked on this design transparency. And what I'm presenting today is not too far from this contributor. So we are going to build models that show the user how the system behaves in various situations. The second contributor is explainability. So if the system provides some explanation why it has made certain types of decisions, then the user is likely to trust it and trust it for good reasons. Because we could also trust a system that is not trustworthy, and that's, as I said, overtrust is a big issue. The third contributor is understandable evidence of safety and security. Those could also contribute to trust. And finally, if the system either looks like a human being or communicates like a human being, both can contribute to trust. So these are different contributors that have been studied in the literature. We try to address at least a combination of those when we study the issue of trust. And that's also very much in line with the aim of the whole program on trustworthy autonomous systems. And I look forward to collaboration with different nodes, including the resilience node in establishing this trust. So two different projects, very brief projects that we have been doing in this area. One is about connected platoons. This is a project we did with colleagues in Sweden and the Netherlands on applying testing to find safety issues in connected platoons. And we showed in that research, which is recently published in a communications conference, it's PIRMC 2020, we showed that existing protocols for connected platoons are not always optimal for safety. So you could, depending on the situation, you could come up with different configurations of those communication protocols, intervehicular communication protocols to maximize safety. That's one project. The other project, which I like very much, and it's still an ongoing project, is about transparency in terms of environmental effect of cars. And we have been looking in particular at diesel emission of vehicles. And we have shown that unfortunately, the design there is far from transparent. So you can observe very, very strange behavior. Of course, we have seen examples of that with Volkswagen and how it was revealed in the media and then eventually was subject to some legal processes. But in our ongoing work, we show how this can be done for different makes of cars and how that could be made into a rigorous technique for making those designs transparent and revealing possible issues with cheating behavior. So I gave a talk, I think a couple of weeks ago in our node about this. This is available through our YouTube channel. And also we have a recent paper, which is not yet published, it's on archive, Catch the Cheaters, which you can download and have a look, where we do extensive tests on a particular car and we study different issues with particle emission in that car. So these are two example issues. I will not talk about them today. I will talk about a different subject, but this gives you a flavor of the different types of research that we perform in our group. We have different types of expertise. So of course, we rely on firm foundations. That's definitely necessary for good research. But we also have expertise in model-based system engineering, in testing, validation, verification. We have colleagues who work on machine learning. We have a very good group of people working on human factors and also people who can analyze data. So this combination is very essential. We also, as I said, do a lot of public outreach. So this is the website where we record some of our media presence and then public outreach activities. And we are also and coordinating this large verifiability project with lots of very good colleagues, including colleagues at York, but also at Sheffield, Leeds, and Manchester. And the idea there is to build a unifying framework to connect different testing, verification, and validation techniques so that we can have a systematic and a holistic view of trust in autonomous systems. So that was the introduction to what we generally do. And now we want to focus more on the topic of this talk, namely adaptive active learning. And in order to make the basics clear, I will talk about active learning in general, and then instantiate it on the two different, say, axes of evolution in time and evolution in space. So let's have a brief overview of active learning. My main area of interest and expertise is in testing. And in particular, I'm interested mostly in something called conformance testing. And conformance testing starts from something called the test model, a specification model, and some test goals. So typically you want to achieve a certain notion of coverage, a certain notion of test adequacy for your test model. So these two pieces of information feed into a test case generation algorithm. And the test case generation algorithm, sometimes offline and sometimes online, in interaction with the system, generates a set of test cases. And by running those test cases on a black box implementation, typically we assume that the implementation is black box, but there are exceptions where you have access to code, for example, or abstractions of system code. You try to reach some verdict about the correctness of the system on the test with respect to this specification model. So what you are basically testing here is whether what is inside the black box is in some sense equivalent to what you specified earlier on as your test model. And this is typically characterized by some mathematical conformance relation. So you specify in terms of a mathematical relation, what kind of systems should be considered correct, what kinds of systems should be considered faulty, and through running those test cases, you try to identify whether what is inside that black box is indeed equivalent in some sense with what is outside of the specification model. So this is the general trajectory that we are interested in. Particularly, we want our test method to be sound, so only reject those things that are not in the conformance relation. In some ideal cases, we also want our technique to be exhaustive, so reject all non-conforming implementations. But that requires some further assumptions that I'm not going to talk about today. The main problem with this trajectory that we are interested in is that as soon as you go to industry and present it to them, they say, well, what model are you talking about? We don't have models. I mean, in best case, we have some Word documents or some outdated diagrams that we drew many years ago, and they are not up to date. You can't use them meaningfully for testing. So how do we solve this problem of lack of models? The solution that people have been using and have been studying is the use of model learning. So you could have a loop which starts potentially with an empty model, or a very rough estimation, possibly an outdated estimation of how the system behaves. It generates some test cases using a model-based testing from it, runs it on an implementation, and then uses those observations to learn a new model. And you iterate quite a few times until you know with sufficient confidence that you have learned about what is inside the black box. And once you have that model, you could use it to test other versions of the system if you do regression testing, or you could use some sort of formal analysis on that model and do all sorts of things. Now you have a model, right, which you didn't have before. Of course, this model is a bit biased by this particular implementation, right? But at least you have something to start with, and you could study it further, identify faults, show it to domain experts, correct it. All sorts of stuff could be done with it. So this is the general idea of active learning. And some years ago, actually, thanks to Amal and co-organizers, we wrote a chapter in a Dutch tool seminar where we tried to give an overview of this connection between model-based testing and model learning, together with Bernard and a few other colleagues. So this is the general picture. And now what I will do is to instantiate this loop with a particular technique that goes back to the work of people like Dana Anglin in the L-star algorithm. And this is best explained in terms of something called a minimally adequate teacher framework. In a minimally adequate teacher framework, that loop that I showed you is embodied in something called a learning algorithm. A prominent example is L-star by Dana Anglin, but there are all sorts of extensions of that already available. And this learning algorithm starts by generating some queries, some very basic queries, asking what would be your output, or are you going to accept if I feed you this input, right? It could be, for example, you have a Java code that you don't have access to in this system. Could be any type of executable. It could be something that runs on a network. You send packets to it. And you send those packets, you call those Java interfaces, and you observe what the system returns, right? That's the first thing you do. You have some idea, some very basic idea how the system is. You feed those queries to the system, and you observe how the system behaves. That leads to some sort of model, some sort of abstraction of how you think as a learning algorithm about the system. And every now and then, of course, you have to reset the system and bring it to the initial state. Sometimes the system doesn't have a reliable reset, and then or reset is very costly. Then you have to tweak this algorithm to do other stuff. So there's a whole sort of learning algorithms that do not use any reset, for example. Then once you have built a model and you're sufficiently happy, so once you generate queries from it and then you feed it to the system, you observe that this looks like a reasonable model. Then you run a whole campaign of tests. It's called an equivalence query that tests whether what you have learned is good enough or not. So that's typically much larger than a single output query. It's a huge number of queries. It could be a random walk in your model, or it could be a more structured coverage of your model that will eventually tell you whether what you have learned is okay. Or if it's not okay, it will give you a counterexample that will be used further to refine the model that you have learned. And you iterate until you eventually get a yes answer, and then you terminate. And then Dana Anglin did also quite some interesting theoretical studies on how quickly this process will converge, and what are the number of queries, equivalence and the membership queries that will be needed to converge, right? So that was the basic thing. That goes back to 1987, and lots of updates have been done since then. Let me briefly show you an example of how this works, and then we will go into the adaptive version of it. So suppose we have a windshield wiper example. And this windshield wiper example is in a black box. It has two possible inputs. So it has a rain sensor that may activate the Viper, and it has a switch which can be turned on and off. And once it's turned off, then you see a different behavior of the Viper, namely it iteratively cleans the windshield. When it's turned off, it doesn't do that, basically. And when it's turned on, it's also sensitive to rain. I'll show you what is inside the black box, just cheating. But then we try to use Dana Anglin's algorithm to learn. So this is what is inside our black box. It doesn't matter whether you think this is a reasonable windshield wiper or not, but it's just an example. You start in the off state, and in the off state, even if it rains, it's not going to do anything. Once the system is turned on, so switch iterative is turned on, then it will have a certain behavior in that state, which you haven't modeled. But another important fact is that as soon as it starts raining, so as soon as the rain sensor returns 1, then you're going to do something different here, and then the switch cannot be turned off. So the switch can only be turned off again if the sensor returns that it's not raining anymore, and then you can turn it off and go there, right? So this is what is inside the black box. We have no access to it. So the only thing we can do is to feed inputs to this black box and observe what the output is. And because initially we have no idea how the system looks like, we can't see inside this black box, we assume that it's a single state. And we don't know what its name is. We just give it an arbitrary name. It happens to be the same name as in the black box, but of course the name doesn't matter here. So it has only a single state, and here I represent that with epsilon. Epsilon means that I haven't fed anything into this system yet. And the only thing I can do is to feed it with my two, say, interfaces, rain and interface inputs, rain and switch interval, and observe what the outputs are. So I feed those into the system, and I observe that the output is 0 and 1 respectively, right? So that will lead to this initial model. My first abstraction based on what I've observed is that if the system is reset, is started, and I do rain and switch iterative, I'll get these two outputs. So this is the first observation table, as it's called, that I observe from this black box. Now, I don't know whether this model is good enough or not, so I'd better look at least one step ahead and check whether this is an accurate representation of the system. So what I do, in addition to starting the system, I start the system and I feed rain into it, and then I do the same observation. What happens if I do rain after a rain, and what happens if I do switch iterative after a rain? What turns out to be the case is that actually doing a rain will not make any difference. I observe the same thing as what I observed before. So far, it looks like I have a very good model of the system. However, if I do the other thing, if I do switch iterative, suddenly, and now my mouse stopped working. Do you still hear me?
Yes, we do.
Oh, interesting. So everything has frozen here. Do you think I should?
Maybe you want to stop sharing and
just
try to share again, Mohammad.
So I'll close my computer and open it. Hopefully that won't take long. You still hear me?
Yes, we can still hear you.
But I can't see anything. So I'll turn it off. It will take 1 minute. I'm really sorry about this.
No problem. We have a few questions to ask. It's
so
called rejuvenation, Bashar.
So can I have a question while Mohammed's restarting his system?
Please, Alex.
Is that okay? So with the testing of black box systems, I'm always kind of a little bit concerned about states that are not necessarily revealed by exercising the input state readily. So for example, in this particular diagram that's on everybody's screens at the moment, I think everybody can see it still. If there was a state that was in there that would only get activated or would only get entered, let's say if the windscreen wipers had operated 10,000 times or something like that. So, you know, you could go from the external spec for the windscreen wipers and you could exercise all the states and you could go through it, but only if you exercised it more than, say, the 10,000 times would you exercise that state that some dodgy programmers put into the system. And I ask questions like that because I've worked with programmers and I know the kind of bizarre constructs that they put in their code all the time because it seems to make sense to them, even if it doesn't necessarily align to the requirements that have been given to them at the time. So it's just kind of a general question about constructs that sit within the black box that don't get tested readily by looking at the spec.
Mm. Is this something you would like to answer, Diego, while Mohammad is away?
Yeah. Regarding these specific situations that are very unexpected, you could say, it normally happens with this setup for the active learning from angling. We rely on the steps for the algorithm, where we build a model that satisfies some properties that I think that Mohammad will show these properties in the next few steps, that they guarantee that you will converge. I think that also already answers one of the questions, one of the other questions from Grisel, that they guarantee that the model converges to a stable model, given the observation that you collected up to some specific point. And then from that part, we rely on the equivalence queries to see if that model is actually correct or not. And this is the step where we should expect to find these situations. But of course, if we assume that a model has, in this case, for example, 3 states, and we have a situation where we need 10,000 specific inputs, that will lead to a very high number of extra states in the model, and that we definitely would pay that during the testing part. It is something that we always have these challenges. But given that we already know that there are some specific traits that lead to these situations, and that is a strategy that can speed up this learning process, which is one of the things that we propose in the technique.
So sorry, I didn't mean like 10,000 states. I just meant that you'd have to go into a particular state, say 10,000 times, and then on that 10,001th time, it enters a different state. So let's say it's at the interval, and on the 10,001th state, it doesn't go to rain, it goes to snow or some other state that is not known from the outside because it's not been observed. And as I say, coders put really bizarre constructs in their code sometimes. And I'll give you as a quick example. It doesn't really relate to this, but I remember on one project that we were working on, a coder put a lat long of 0.00000 as a failed value. Well, everybody knows that there is such a place as 0.00000 on lat longs. You know, we're talking about latitudes and longitudes, but he did not consider that it was ever going to be that and put it as an error value. Okay, so what people think, what people put into these constructs don't always make sense. And so I just wonder how, you know, we can test for things that don't necessarily make sense, the nonsensical constructs that people put within the black boxes, that when we're observing them from the outside, we might not observe in everyday testing and everyday exercising of the states that we're expecting to be there.
We for learning a model that describes this specific situation, we should expect to have a model that is different from this, that won't have 3 states because there are some extra states that should be represented there. But if you assume that you have this specific model, you can always use some stress testing techniques that you can apply random queries and see if something happens apart from it is specified in this in the model. It's one of the ways that we can use these techniques for stressing the system under some very high number of random queries and see if something different happens. This is one of the ways that we can rely on learning to see these situations.
So sorry, I apologize sincerely about what has happened. I don't know what happened, but I was frozen. Do you hear me now?
Yes, we can.
Yeah, so I think that's a very interesting question, and I was trying to follow. I was trying to guess what the question was from the answer. So I think the question is about testing mostly and rather than learning. So how can we basically do some sort of exhaustive test to make sure that we encounter those very rare situations, right? And there is quite some work on exhaustive model-based testing. So assuming that you expect certain types of faults to happen, how can I generate test cases that exhaust all those cases? I think we can have a discussion about those techniques. There have been some even recent work on in that area. But testing is by nature, unless you assume some sort of fault model, non-exhaustive, right? So if you don't have a good notion of what kind of faults you want to detect, then you are not going to be able to detect all faults using testing. You have to use alternative formal verification techniques.
Yeah,
but we can have a discussion. Yes,
sorry, I kind of led it off track. I'll let you carry on. And it was about the learning bit really more than the testing thing. It was how can you learn the model if you don't know whether you've exercised all the internal states?
Yeah, I appreciate that, but learning has a testing component in it. And once you learn something, that equivalence query that you pose to confirm whether what you have learned is indeed what is inside the black box very heavily relies on the testing technique that you use to confirm that model, right? If your testing technique that generates the equivalence query is an exhaustive testing technique, then you are likely to recover those type of very rare situations and improve your model. If your testing technique that generates the equivalence query is a random walk, then of course you may miss those cases and not find them. I don't know whether I answered your question to some extent at least.
Yeah, thank you. Let's carry on.
Yeah, we can
Distracted
come
for
back to
longer.
that one.
Yeah.
So I was explaining that upon providing the system with this other inputs, which is one step ahead of what I've learned, I suddenly realized that I received different outputs with the same stimuli, with the same tests. So this indicates that my initial assumption about a single state model was not good. And I keep on refining this by looking at those counterexamples, enriching my state. So I now find out that doing a switch iterative will lead to a new state. So I'll enrich my state space by saying, okay, rain is this in the same equivalence class as epsilon, but switch iterative is a new state. And I keep on doing this, analyze my counterexamples until I reach a model, and I won't spend more time on these intermediate steps, until I reach a model that is both consistent and complete. Consistent basically tells me that when I look one step ahead from the states that I've already discovered, I won't see anything new in terms of output. So if I feed the system with the same tests as before, looking one step ahead does not lead to any new output. And the complete tells me that if two states were equivalent, so epsilon and rain, for example, in the previous slide, they were considered equivalent, then once you extend them with new input, you will not be able to distinguish them. So these are the two important properties of this observation table. Once you have that, then you have some confidence that this is a good abstraction. Then you start your equivalence query. And then your equivalence query may reveal further issues, right, in the model that you have learned. Although this is consistent and complete, it only looks one step ahead, while equivalence query may look, as you said, 100 steps ahead. So you pose an equivalence query, which is quite heavy, and then you process the counterexamples and then analyze them and refine this until you reach a consistent and complete table that is not violated, that is not falsified by your equivalence query. So this is Dana Anglin's L star. And we now want to go one step ahead in two different directions with respect to Anglin's L star. One is about evolution in time, and the other one is about evolution in space. Evolution in time is when the system evolves, for example, due to further development or due to a learning process, so it changes its behavior. And the evolution in space is when you have different configurations of the same system. So let's look at evolution in time first. Are there any questions before I move on? How am I doing in terms of time? Okay, half an hour. Any questions?
There's been some discussion in the chat, so if people want to
yes, please
ask their questions, this would be a good time.
I think there was early on you mentioned transparency and explainability,
right.
And I think I made an assumption of what I thought you meant there. Somebody else asked the question, so maybe if you could just clarify the difference between transparency and explainability.
Right. So transparency typically is about making the design intentions, explaining the design intentions basically to users, right? So if there is something that is hidden in the design, you would like to make it known that, for example, the system has been tested in a certain way, or the system is supposed to behave. The example that I gave you for transparency is if the system produces an enormous amount of particles in certain scenarios, you have to document that and show it to the user before the user, for example, buys such a system. If your laptop is going to force you to use a certain type of adapter, then this should be documented and presented to the user before you buy that system, right? So likewise, for an AI system, if it's designed to have a certain bias, this should be documented, right? Explainability is typically about the runtime of the system. So once the system takes a high-level decision, it had better come up with an explanation why it made that decision and present it in an understandable to the system. So in my terminology, transparency is mostly about design, and explainability is more about runtime decision-making, particularly high-level decision-making of a system. Does that make sense?
Yeah, that makes perfect sense. Thank you.
Thank you. Any further questions? Shall I move on? Okay, so let's look at the same system and assume that it has evolved in time. For example, what was inside the black box now suddenly has a new feature in it, or a new type of behavior in which you can permanently turn the wiper on and off. And you're not aware of that. So the system has evolved in time, but you're not aware of how it has evolved. And in order to learn this new system, you could do two different things, two different very extreme things. One is to throw away everything that you knew about the original system and start building everything, all that was in the observation table from scratch. That would be a shame because you knew already something, and it's likely that some of those behaviors are still present in the new system, right? The other extreme is to rely solely on the observation table and then start expanding that further and exploring that further. That could also be dangerous because there could be certain states that are now merged together. So that certain distinct states in the original system that are merged together, or certain tests that are not distinguishing anymore in the new system. We call the first category of states that are merged redundant queries. So the queries that are in the new system not necessary to be made because now the system has fused some of those old states together. And we call those tests that are not useful anymore deprecated tests because they are not useful in distinguishing states. So what we try to do is to reach a balance by analyzing those redundant and deprecated queries early on with respect to the old table before we start extending that with, for example, new interfaces that the system provides. Once we have a solid basis to start, then we run L-star as before and we relearn the system. But based on the information that we know is valid still in the updated system, right? So these are the two research questions that we ask for evolution in time. One is, how can we learn efficiently about the evolved behavior? And the two principles that I explained are main two attacks to learning efficiently. So making sure that the states that we rely on exist indeed, and they're indeed different in the new system. And also the tests that we use to distinguish states are still valid tests. And the second question that we ask, suppose we come up with an algorithm for adaptive learning. We want our algorithm to be robust in the sense that if we learn a system that is the result of a couple of steps of evolution, we don't want the learning time to explode exponentially compared to a system that has been evolved very recently, right? We want the learning time to grow only reasonably with respect to the evolution time, and that we want to also analyze in our research. So this is very old research. There are a couple of very good papers already in the field. So Alex Gross, Doron Peled, and Yanis and Yanakakis have an algorithm to start with. Then Chaki, Clark, Sharigina, and Sina came up with an improvement upon that. And basically, this work of 2008 is the state of the art in this field. They are very minor. No, I shouldn't call them minor. There are other extensions, but this algorithm is the backbone of what is out there. There is a recent paper by Jakob van der Poel and associates, which studies some of the problems with Chaki and Clark's algorithm, but this remains the state of the art, and hence we compare our results to their algorithm. So remember the two principles of our technique. One is to first check whether any of the states that we had in the original system are redundant in the new one. And we do that with respect to the tests that we already had. We only extend it with this new interface that the extended system has provided. So remember, we had rain and switch interval in the old system, but the new system in the course of evolution has provided one additional interface, which we include in our tests. Oops. Which we include in our tests. And then we check whether the old states are valid or not. And to do this, we do basically a depth-first search in a tree-like structure where we look at the test results with respect to this slightly extended set of tests. And we stop the search, we terminate the search as soon as we find all the children have already been visited before. So that from that point on, we know that we are only observing redundant states. And this is the result of doing this cover set, finding this cover set for the new system. So this will give us the states of the system. So we have the empty input, the switch interval input, the switch interval followed by rain, and the switch permanence input as the three prefixes that designate the four states of the new system. So that will be my rows of the new table, the initial rows of the new table. Then in order to find out what the columns should be, I check whether I can come up with a new set of tests that I can still distinguish these four states that I have found. So I remember I found empty, epsilon, switch interval followed by rain, and switch permanent. And I try to distinguish them with as few inputs as possible. So I do a breadth first search in this tree, and I terminate until when I find that I can distinguish all four of them using a minimal number of inputs. So these are the two main stepping stones of my algorithm, and the rest is just basic L star. So by composing these three steps, I come up with an adaptive learning algorithm. And in order to check how useful and how effective this is, we applied it, so Diego Adenilson and I applied it on an OpenSSL implementation, which had quite a few different versions evolving over time. And actually, the router has already done a very good job of applying L star on this. So there exist already finite state machine models of these OpenSSLs. And we verified these two research questions on this OpenSSL implementation. First is, how efficiently can we learn this evolved behavior? So how many more queries are we posing with respect to the brute force L star algorithm that throws away everything and neglects everything? And the second one is, how sensitive is our learning effort with respect to evolution? So how much more should we spend on learning if the system has evolved over time? And these are the results briefly. This is our algorithm, and this is the state of the art by Chowkey and Clark and associates. You see some of these numbers are negative. So this is the comparison of the amount of effort we should spend with respect to the brute force L star that neglects everything. So ideally, we should always be in the negative. If we are in the positive, then we are actually spending more time than brute force. And if you see our algorithm, at least for this particular example, is on average in negative, so it spends less effort than learning anew. Of course, as you go by and then the system becomes more and more outdated, then there is less to reuse, so you go more towards zero. So that's one thing. While unfortunately the competitor is not doing very well, so it's almost always in the positive, apart from some very initial updates. The second thing is that our algorithm remains more or less constant. I mean, it does grow. If you look at the average, it does grow a little bit, but it doesn't grow significantly, and it reaches zero at the end, more or less. While their algorithm actually goes quite significantly. And note that the scales are very different, right? This is 800, this is 50. So there is quite a few factors. A couple of orders of magnitude, one order of magnitude difference here, at least in this scale, right? So you see a significant saving when you apply these two basic ideas in the order that I mentioned while you're doing adaptive learning. Are there any questions before I move on to the next topic? How much time do I have? So I think I will spend like 5 minutes, 6 minutes on the next topic, and then conclude. Is that okay, Radu?
That is perfect. Thank you.
Any questions before I move on?
Maybe on the previous slide, Mohammad,
Sure.
Can you explain a bit better what the horizontal axis means?
Right. So the horizontal axis is the temporal distance from the original version, right? So it's in terms of years. So this has evolved over quite a few years, right? We look at a version that is very recent with respect to the base version, and then we go all the way up to, say, I don't know how many, I think we had 18 versions of evolution that we took from different years. And the vertical axis is the difference in the number of membership queries with respect to learning from scratch, right?
All right, so that these are real-time years and how they updated this?
Don't remember exactly whether these are. I think these are years.
It is.
Yes. Okay.
This is basically the distance between the version that you are learning and the version that you reused. Yes. And that goes from 0 years, which is the learning with your own version, and 15 years, I think. 15 years.
I think it was a bit more, maybe 18 years. I don't remember.
18 years, 18, 15 years, something like that.
May I ask a follow-up question?
Sure.
In terms of time, we all know that software systems don't evolve linearly. And I noticed there seems to be a bit of a step at 5 years.
Yes.
Is that because there was a major release at that point with a lot of change?
That's a very good question. That is a subject of a subsequent research we are currently doing. So what we are trying to do right now is to categorize different types of commits on a repository, and then using that optimize our adaptive learning algorithm. So if we have a bit more information about the black box, we can definitely exploit that when you're learning about new things. So sure, that's a very good question. Absolutely. Okay. Good. Okay, so very briefly about the last bit. So I'm sorry for people in software product lines and people interested in variability. I will be very brief about this. So far we talked about the horizontal evolution over time. So when you have new versions of the system that change for different reasons, for development, for learning, for whatever purpose. But as I said, systems also tend to have many different configurations. For example, they could be deployed on different platforms. They could comprise different features. And we also want to learn about all these different features. So we pose these two main questions. How can we learn about the changes in the space by making a succinct model that summarizes all those variability space in features, in deployment environments and things like that? So how can we come up with models that are succinct and summarize all those changes in space? The second one is, we want to learn about these changes without exhaustively going through each and every product. We want to learn this by only sampling a few of the whole different points in the variability space. And I will be very brief, as I said, because I'm running out of time. The results can be seen in a recent journal paper in empirical software engineering. And the idea is that you learn from a few different products, and there are different ways of selecting those products. I will show you in one picture how this will influence the learning process. And then we have an algorithm that looks at these learned models and tries to fuse them, tries to summarize them as much as possible by annotating the behavior with the commonalities between these different models. So we basically annotate the different transitions by saying, okay, this belongs to this and that feature because it comes from the products that have these features in common. That's how the algorithm works. I will not go into the details. I will just show you some of the outcomes of. So basically what we do, we take different models and then we try to relate the different states. Oh, the state is likely to be in this one because the behavior that I've learned looks very similar. And by the way, I should acknowledge this builds upon a very good piece of work by two very good colleagues, Neil Walkinshaw and Kirill Bogdanov at Sheffield. They've been working on this for quite some years, and we used a lot of their results in this algorithm. Right, so we try to identify similar behavior, fuse them together, merge them together, and come up with a model that summarizes the commonalities and makes a succinct model. One very important question is how to select those products. So in the software product line community, in the variability community, there are many different algorithms that are used to select products based on the coverage of the features you are interested in. So if you select products in such a way that each feature is present in at least one product, then you are doing one-wise selection. If you look at pairs of features, then you're doing two-wise selection. It can go on. You can look at tuples of size 3, 4, and it can go on. And of course, the worst case is that you exhaustively look at all possible combinations of features. So basically generate all products, which is impossible in practice. Now, the question we addressed is how sensitive our learning algorithm is with respect to the different products that we choose. And I will just show you a couple of different results. So we took some typical examples from the product line community. And we first looked at this summarizing behavioral algorithm. So this is the sum of the models that we learn individually, for example, using L-star, or it could be also using adaptive version of L-star. And then this is the result of a summarization. So as you see, we do quite a good job in summarizing the outcome. Actually, in some cases, it's very drastic summarization. So if there's a lot of reuse among different products, you're likely to basically squeeze them into very small models. So that's one thing that I want to communicate here. Again, just to be sure, these are individual products, and this is the summarized behavior. And then when there is a big difference, it shows that our algorithm does a good job in identifying commonalities and squeezing that into a small model. So that's one message that I want to communicate before I conclude. So the larger this red line is, the better our technique is working, basically. This is the effect size of our technique. I will skip this one. The other thing that I want to communicate here is that we reach actually a very good precision. So the vertical line here is the precision of the learning. Getting 100% accurate means that you are basically learning the exact same behavior as all the products, while here I'm looking at the different sampling techniques. So one-wise is a very weak sampling techniques where you have at least one product for each feature. And it goes on. What we see here is that two-wise sampling does a very good job in almost all cases. So we get very accurate models, very close to say 100% accurate by doing two-wise sampling. There are very rare cases that you need three-wise sampling to get better results. So the take-home message is that in the examples we have seen so far, two-wise sampling seems to be doing a good job in selecting the products and reaching a very good accuracy of the combined model for the rest of the products that we haven't seen. With that, I would like to conclude the talk, and I would be happy to answer any further questions you may have.
All right, questions for Mohammad?
Thank you very much. I have a question about how this might be extended into systems where our transitions are probabilistic rather than the state-based models that you've shown through the talk so far. How might that work? I think it comes a little bit back to what Alec was asking earlier about going to a state and not always coming out in the same way.
Yeah, so there are all sorts of extensions of All-Star in different directions to learn richer models of behavior. There are a handful of extensions for things like time, continuous dynamics, probabilities, and distributions. And yes, so there are algorithms that you could basically plug into our technique and apply the same idea of reusing as many queries as possible when you're applying it to adaptive systems. So I expect you could use those algorithms. And the other thing is that typically when you want to learn more about those complex phenomena like probability distributions or continuous dynamics, you may be combining some of these active learning techniques with passive learning techniques. So you may look at the trajectories and try to do some regression analysis to for example, find if you have some idea about the distribution of your phenomena, you could try to do some regression analysis on the data passively to find the parameters of your distribution, things like that.
Thank you.
In terms of scalability, oftentimes we apply ensembles of models, and I wonder whether or not the approach that you're describing could scale to ensembles of models, because the way that each model works might provide an overall different effect when it's part of an ensemble.
So I'm not sure if I understand the concept of ensemble very well, but one ongoing research that, again, we are doing in our group and with a few students is to do some sort of compositional learning where you know something about the components inside the system and how the behavior is distributed in your system. And you try to focus the learning of those individual components by first assuming that there is some degree of independence among those behaviors, and then testing that independence when you're doing some sort of equivalence query. I don't know whether that answers your question, and this is the thing you were, this is the notion of ensemble you have in mind.
Yeah, so you kind of touch on where I was driving at really, and that is that because of the complexity of bringing a number of models together and the emergent properties that you might get out of that bringing together of the models, they may be designed to be independent, but actually you might get some emergent property that comes out of them all putting together. And I wonder how well, or whether or not such an approach could tease out that emergent behavior so that you can avoid it down the line.
Yeah, so there is an initial paper by a colleague of mine at a different university, at Eindhoven University of Technology. And also one of the students of Fritz in Nijmegen. They have been working on similar problems. The problem you're mentioning is indeed very prominent. How do you test that those independence assumptions that you made while learning the individual component is valid? We are working on along that line together with those colleagues, and we have some initial results. We are proving some stuff. We are still at the beginning, but I would be happy to share the initial results by other colleagues with you if you drop me a line. So there are some initial work in that along those lines.
Yeah, that sounds really interesting. I'll be very interested. Thank you.
Thank you.
Any other questions? Would you like to ask your question, Reza?
Yes, sure. Thank you so much for the talk. It's really interesting. I have a small question. When you're talking about the learning process, I was wondering if this algorithm is useful for different case of studies. How would you compute the amount of time that this learning process needs to be done?
Sorry, I missed your last sentence.
Considering probabilistic behavior, some systems.
You're breaking up a little bit. I missed a couple of your last
different systems would require.
Could you repeat the last few sentences? I couldn't hear you. Sorry.
Yes. If you're considering, or if you would consider probabilistic behavior, how would you compute the amount of times that you require for the learning loop to get the specific probability?
Yeah, so this is something very recently I've been looking at. So in particular, Diego was looking at that learning of probabilistic systems. We don't have any definitive result. There are some earlier papers, but unfortunately, this is something that we have been doing very recently, and I don't have any definitive result. It very much depends on how much you know about the distribution you're learning, right? So if you know that the distribution is, for example, normal or Gaussian, then you can, of course, this converges much faster than when you don't know much about the distribution, right? But I don't have a definitive answer. This is something we have been exploring recently, and maybe Diego can say something, but it's very early on. We can't say much about that.
Okay, thank you.
Diego, do you want to say anything about this, or?
Yeah, we did a couple of experiments on this line, and there are some really basic results that we had, but we still have a lot of progress to do on that. I've seen some works on learning probabilistic automata, but we were mostly on passive learning, which is another branch of learning technique. If you want, we can send you some pointers for that, but they're mostly focused on this line of research.
I was just going to ask a question that brings me right back to some of the early slides you mentioned there, which was about transparency and explainability. If we have a nice transparent design process, how might we involve the knowledge that we have in that into the black boxes? Are there any ideas we can do that? And secondly, Alec mentioned scalability, which I think we all know is a problem for these kinds of approaches. Are there any thoughts you have on how we can maintain explainability with learnt black box models?
Right. Difficult questions. I mean, these are very big questions to address. So if I understood it well, you were asking in the first question, how could we kind of incorporate these design intentions into the documentation of the system? Is that what you're asking?
Yeah,
or?
absolutely.
Yeah.
So we may not have the detail of the software, but hopefully we have something from the developers that gives us the intent of the system.
Right. So what I was, what I have been doing so far was to come up with a set of a parameterized set of tests that explain the different behavior of the system in different situations. For example, when we were looking at the particle emission of cars, what the current test regimes, the current test cycles for emission do, they basically look at a single type of behavior. They say, if you do first an urban test like this, then a motorway test like that, and then you see that the total emission is below that level, then you're fine and you pass the test, right? So if you could characterize so if you could document the design intention in a much richer fashion than just a single trajectory, but you specify in a whole lots of pockets of trajectory, saying that, okay, not only in this single test, but in all those urban cycles that look like this, followed by all those motorway cycles that look like that. This is how the particle emission should be or works actually in a particular brand of car. That's a much richer model, and you expose much more useful information to the users. The same for example, fuel consumption, right? Now they say the fuel consumption is so much liter per mile. That's not very useful. I would like to have a much richer explanation that says, okay, in these types of circumstances, this is going to this is how the fuel consumption looks like. So my research agenda so far has been to have a description of tests that is rich enough to go over pockets of behavior that look similar, and then have a whole range of them that look sufficiently different to characterize the behavior of the system, right? This is one type of say documenting the design intention that I've been after. I guess similar technique could also be used for explanation. So instead of providing one counterexample or one example of behavior, if you have a whole pocket of behavior as explanation of how the system behaves, then that, for example, as a causal explanation of this type of phenomena caused this type of effect, then that could also be a nice way of explaining stuff. So we were actually looking at causality as a particular way of providing explanation of this sort, so looking at pockets of behavior that can lead to another pocket of behavior as effect.
Okay, thank you.
Sorry, it's a bit vague because
no.
They're big questions, so answering them.
Yeah, absolutely, they are.
All right, so maybe time for another big question, I believe, from Wahid.
Oh yeah, thanks for the talk, Mohammed. Yeah, most of the time we have these like software agents in collaboration with human agents. Like if you go back to the idea of trustworthy autonomous systems. So how do you think we can get humans involved in this problem of verification? Or can we learn from verification problem like in isolation just for softwares, or what aspects we should take into account? So
the idea in the verifiability node is to perform user experiments in order to come up with human models, right? What we are after is to have some initial user model which specifies very crudely how typical users behave when they are confronted with an autonomous system. And then while we are verifying the system, we observe the user and see how crude our model was and start refining it. Because first of all, as I said, our initial model might be too coarse, too crude, and not specific enough for the users. And secondly, users may change their behavior when they're confronted with an actual system, right? So the idea of the verifiability node is to start modeling the user behavior, but also evolve the user modeling as we go in the verification process. So involve the user in the verification process, observe their behavior, and refine the user model, and use that as part of the verification process as well, right?
Right, thank you very much. Yes, this is a wicked problem, Bashar.
So can I, sorry, Radu, can I just ask something on that?
Please.
So do you think then that we would need to have a different, a unique human machine model for each individual that works with a modeled system. So actually, you know, it will be a system that gets modeled and updated as we evolve our relationship with the machines that we work with.
I think you have to identify, similar to the question that I think Colin just asked, we need to identify different classes of users at least, right? So for example, if you're developing some healthcare robot, then I think it should be able to deal with different types of people, including different patients in different age range, for example, doctors, nurses. So I think you should classify different types of users and at least have some model of their behavior. I appreciate that there is still quite a variability even in single class, but I think that's our starting point, identifying behavior of users that look to some extent similar, and then specifying them, using them for verification, because currently none of this is being done, right? If you ask a roboticist, it's likely that they don't use any type of user model for verifying the robotic design, right? So having some classes of user behavior for different types of users, I think is a good starting point in my view.
And maybe for each class, you would use the most conservative model you can.
I mean, then you have the issue of balancing how useful the system is with respect with how safe the system is, and that's a delicate balance.
Yeah.
Yes.
We've done a little bit of work on the identifying different groups of users by behavior. And one of the challenges is actually having distance measures between those groups. So how to identify whether a user falls into an existing group or is a new class of user.
I think that's a very interesting problem. I would be very interested to know more about this. So if you could send me some pointers and we could have a discussion later on, that would be great. Yeah.
Right. Thank you very much again for the nice talk, Mohammad, and for generating all this interesting discussion.
Thank you very much, Radu.
Thank you everyone for participating and for asking questions and providing comments. And I hope to see you at our seminar in 2 weeks' time.
Thank you.
Do stay safe until then, and talk to you soon.
Thank you.
Thank you all.
Bye.
Thank you all very much.